Hi, good morning. This is Piotr speaking, and that's Quasar Training Part 7, 2020 update. And in this part, our primary topic is what happens when we have more than one Quasar class, and how do we relate classes to each other. So in the example so far, we worked with just one class, with the motor class, but often, or I would say maybe even always, we need more classes. We need more classes because life is complex to that extent that rarely it fits just one class. And for an example here, I'm showing a Quasar design diagram of a rather advanced Quasar-based OPC-UA server. So as you can see, there's quite a number of classes, at least, I don't know, like 15 or maybe more. It looks like actually more than 20. So they are organized in like a tree-like structure here. But anyway, my message is this is a sample of a real-world project OPC-UA server made in Quasar. So as you can see, it's not that trivial. But of course, maybe just to answer the question, why do we do that? So we organize software in classes, in Quasar classes, for the same reasons that we use object orientation. So we want to have a nice separation between different unrelated parts of our system. We want to encapsulate state. We want stuff like that. Quasar classes and OPC-UA, of course, is not directly related to object orientation, because object orientation really talks on how to organize the code, the source code. It's more for software engineering, while Quasar classes actually more represent the state of real control systems or information exchange systems, but still there's a lot of similarity. So when we think how we can organize multiple classes, we of course can have something like side by side, so completely unrelated. But since a Quasar server can have multiple classes, as we've been doing a class with motor, we can as well imagine that our server, for this reason or that reason, for a commercial reason or for any other reason, will have a few unrelated classes, like a motor, where you will provide OPC-UA interface to motors and I don't know, generator and a valve and whatever. And it's maybe not that obvious why you would put a valve and a motor in the same OPC-UA server, but still it's possible, and there might be a client wishing that. So this is side by side. But then much more common in control systems that at least I've worked with is some sort of parent-child relation, and I loosely call it vertically because this is how it looks like in Quasar design diagram. And then what we see is we represent that something is a part of something, and this we often see in real life. It's a classic example really from object orientation, so that a car is composed of an engine and a gearbox, and then you look at the engine, it's further composed of, I don't know, cylinders and crankshaft and stuff. So this is being part of a composition relation between classes. But you can also think of other similar relations which will look very similarly in Quasar, but the semantics, the meaning will be different. For instance, representing being organized by, like being organized by physically or by connectivity or something. For instance, if you design some sort of information exchange system where you see how different local networks form together bigger clusters and bigger networks, and finally the internet, you could say that the local network nodes are children of a router, which is, for instance, a parent. Yeah. So if you look at the data path between a local network and the internet, clearly a router seems like a higher instance. So that was just a bit of theory. And now the question is, how do we actually achieve it in Quasar? So I'd like to show you, actually I'd like to modify the example that we've been working on so far. So we just set motors. And I'd like now to make a hierarchy. So we said that our system is like intelligent motor controller, but now we've been kind of assuming that the motors were kind of living on its own, but means there was not a controller a class, but now I will fix that. And I will actually add a controller class that will be a parent of all motors. Yeah. And then I will assume that motors can have a variable number of temperature probes or airflow probes or something like this. So what do? I will need to add at least 3 new classes. Okay, so simply add child class, and this we said should be controller. And then we said that we want also temperature probe and airflow probe. No. Okay, airflow probe. And I will remove those cache variables. I don't really need them at this moment. They were just kind of added by Eclipse to help me filling the contents. So I have a previous motor, that's this class. Okay, I can see here it's motor and the three new classes. And so I said that in relation to motor, the controller will be its parent. Okay. Now, how do I express this? Before, maybe you remember, I think part 2 and part 3, we've been adding has objects from the root of the server. And the same rule applies to relations between classes. So I go to my controller class, which will be my parent, and then I say add child has objects. And I'm saying that controller has motors. Okay. And then I said that motor should have a possibly variable number of temperature probes, for which we already have a class. So temperature probe and has objects again, and airflow probe. Voila. And the last part is, in the original design, I said that from root our top level classes below root are, originally they were motors, but now I will change it to controller. Okay, so in other words, I kind of shifted or rotated the hierarchy. So let's maybe have a look how it looks like. Generate diagram and then PDF viewer. And this is the situation at this very moment. I will need device logic for my examples, which I forgotten to add. So, by the way, this DL stands for device logic, which means those classes don't have device logic. So, I will add this as well. Class temperature probe. Okay, so now we have device logic. What I basically did right now is, from motor being directly under root, now motor is under the controller. And from cardinalities, we can say that the server can have any number of controllers, and each controller can have any number of motors, and motors can have any number of temperature probes and any number of airflow probes. Okay? So now let's see how the situation impacts impacts other things. Now, first of all, let's try to build it. And I have a feeling that, of course, it will not work because, first of all, we added new classes and we have to generate the initial device logic. So for controller, for temperature probe, and for airflow probe. All right, and then it's a sour fail. Now, again, I think it was pretty expected because now I completely reshuffle the hierarchy and no longer I will find motors under my root, right? So let's make that a simple fix. So this is the piece of code that we wrote very early in this training. So that was the main loop of Quasar server. So there we've been referring to the motor device logic, but now I'd like to actually do the controller device logic, which is a simple change. So instead I will do just controller and okay, controllers, this should work I think, and controller update. And of course what's missing here is I don't yet have this controller update method, so let's add this as well. It's actually very similar to what we did with motor beforehand. So that would be controller, and then we'd have controller update, and inside here I will do what I did before, which means I will basically iterate over all motors. So let's maybe look at the design diagram because this is actually kind of important. So previously the root only contained motors, so I could say, hey, where's the root, and give me the list of all motors. And now what I do is from root I say, hey, give me the list of all controllers. On each controller I call update, and then from this update I will iterate over all motors and I will call update on every possible motor. Okay, so what I do here, and here comes something new. So here I will take motor, and from motors update, voila, and let's try it out. So what's the new thing here is, well, first takeaway from this part I think is that whenever we are in device logic of any of the classes, okay, and we want to get a list of configured device objects for any children classes, we can use those functions like motors in the situation. So we're in controller, so in controller we can ask motors and will give us the list of all motors. Similarly, if we are in the device logic of motor, we can do temperature probes or airflow probes, all lowercase, and that will give us the list of all configured temperature probes and airflow probes per this particular motor. Okay, so that's the first important takeaway. Anyway, probably so the behavior should be different, but let's see if the server actually starts, and I think it will not. And why? Because, and now comes the second important learning item here, is that the layout, or let's say the schema of configuration file follows the design. Okay, which means that before in the config file, and a small recap, the config file is where the executable is. So before we had the motors at the very top of, just under configuration. That was because just under configuration we had motors, but now just under configuration we have controllers. Okay, so this no longer makes any sense, and of course, rightfully, the server complains that this configuration does not make any sense, and you can also see here that the content model is controller, right? So, the weird thing though is that Eclipse is not letting me add the motor here, and this is because this content is already broken. So Eclipse is very much confused, as you can tell from here, because it's saying invalid content. That is expected. So I'm just gonna wrap it with a controller. Say controller 1. Voila. And now let's try to run it. And what I see, we basically get the same thing as before. And it's maybe interesting to have a look on how it looks like in Eclipse. Sorry. It's interesting how it looks like in UA Expert, that's what I meant. And what did I do wrong here? Voila. Okay, and now you see we have controller 1, and then under controller 1 we have our motors. So this is another learning point, important learning point, that address space also follows the design. Okay, it does follow the design because now in the address space we basically see the kind of the replica of the hierarchy we have here. So it's important to understand that what you have in the design and the hierarchy of things follows or propagates to the configuration file schema, but also to the address space. Okay? So now let's talk on which we had a look at already. So we've been talking about navigation in device logic. So what I use here in my device logic of controller is that I can do motors, right? And I get a list of all configured motors and call whatever method I wish on them. And of course, since a motor has temperature probes and airflow probes, well, I can also expect that I will have temperature probes and airflow probes. I think I'm actually repeating myself at this point. I think this I mentioned. But what is relevant here is, in most cases, we can also go from bottom to the top, which means when I'm in a child class, and this here my child class would be, for instance, a motor, because a motor is a child of controller. If for some reason I need to access an information from controller or call a function on the controller or whatever like that, what I can do is I can do get parent, and get parent will return a device logic of controller. So in other words, get parent will return me this object. Okay, the object of this class. Okay. So this is how you, so now I think it's explained how you can actually move up and look what's up, and also move down. With one small print to add is, which I actually, okay, we will have a look at this in a second, because there's one corner case for the situation. Good. So what we did so far was to organize classes in some sort of hierarchy. And that was, as we said, for instance, now we have a controllers and motors. So this is better organized. So because imagine a intelligent motor controller can handle up to few, let's say 4, maybe 1,100 motors to control them nicely. So this is simply better organization. What we achieved here is better organization, and the Quasar design looks more like the real system, and it has a lot of advantages. Then we have some corner cases. So we have situations when a class can have multiple parents, and a class can also have cyclic reference to itself. That's not really a big deal. But let's have a look at this. So now imagine that I will add a side-by-side class, which let's look at our diagram. So we are somewhere here, and I will imagine it's a commercial request that we have this nice, server for intelligent motor controllers, but we also now have to support an older product, which is, well, not that intelligent, and that we have some direct interface to the motor without the controller. Doesn't really matter. It's just to illustrate the design problem here and not only the motor control problem. So my new class, since the old generation motor is completely different in behavior in the data model from this motor, I'm adding a new class to support this old type of motor, and I will simply add a class called old type motor. Okay, and I think it should be supported directly from the root of the server. Okay, so here I have old type motor. Okay, and now if I regenerate my design diagram, it looks like that. So far so good, no big problem. Okay, it's just a side-by-side class, and now we interpret it this way that the server can have like two independent let's see, types of things. Of course, at the same time, that's possible, and it can have both the new generation of like intelligent motor controllers with a controller, a couple of motors, and a number of probes, and the old type motor. Okay, but now what I'd like to say as a part of the corner case, imagine that this old type motor actually uses the same type of, for instance, temperature probes. Okay, so the temperature probe has exactly same data model. Maybe it's even coded the same way, means it has the same device logic code and stuff like that. So, of course, I don't want to be redundant here. I don't want to make a temperature probe for all type motor class or something like this. That doesn't make sense. We should be clever here. So what I do, I will say that all type motor can have any number of temperature probes. So here I add has objects and temperature probe, voila. And then look what happens. We get an entirely legal situation that temperature probe, if you try to identify who's the parent of that class, you could say it's both all type motor and motor. Now, it creates an interesting problem, that is, device logic of temperature probe. Since device logic is a C++ class that follows a given Quasar class, now we cannot anymore say that this is a class motor or class all type motor, because it can be actually any of those classes can hold temperature probe. And then this is the corner case in which get parent approach will not work. Okay, it will not work at all, and then the only way to kind of go around this problem is to actually establish this relation by not going from bottom top, but rather from up down, with up down approach, which means if we want something from the temperature probe, we instead go from here down, because we can always iterate all temperature probes from all type motor as well from motor. But in this situation, we cannot say what's the parent type because there are multiple parents. Okay, so we just kind of invert the problem. But still, usually it doesn't really complicate device logic. It's something to mention because it's maybe less obvious. And last interesting thing to mention. So, in fact, the power of has objects is that you can have a lot of very different relations here. So you can make cyclic relations. So you can say that temperature probe has objects of temperature probe. I have no idea what that would mean in the real life sense, but we have situations for other types of things where this actually makes a lot of sense. It's like matryoshka mechanism, when one identical thing can be contained in another identical thing. Maybe the size is different, but you know the matryoshka thing. You can also say that temperature probe has motors and motors has temperature probe. I don't know again what would be the use case for this, but there's a lot of power here, and you can of course use that power. You can harness that power for your for organizing your classes. Okay, so that was part 7 on organizing classes. We had few takeaways here, I think. We said why we organize classes and why we often need more than one class per server. We looked at side-by-side organization. So side-by-side is what we more or less had here, that we have controller and side-by-side all-type motor, or airflow probe and temperature probe. Then we've been looking at building some parent-child relations, so kind of vertical organization, which can represent being part of, but also being organized by. And voila, see you in part 8.